Relativity theory challenges common sense, and we've seen this in two different situations. First, where there's a clock that is moving fast, so its speed is comparable to the speed of light, that clock runs slow. It runs slow according to the clock which is at rest. Secondly, we've seen that if there's an object that is moving, let's say moving towards you, then you will see it as shortened in the direction of motion. There's a third, very non-common sense kind of phenomenon. Suppose that two events happen, one here, and they happen at exactly the same time, according to me. That is, they are simultaneous. But if you are moving with respect to me, then you will not see these two events as having occurred simultaneously. In other words, simultaneity is relative. To understand this, we must first understand how the clocks in any given inertial frame are synchronized, that is, they are set to a common value. So let's do that first. Let me begin with the perfectly obvious point that light needs time to travel a distance, any distance. If it's a small distance, less time. If it's a bigger distance, more time. That's because the speed of light, although it is very large, 3 times 10 to the power 8 meters per second, is not infinite. So, suppose that we look at light that comes out from the sun. Well, that light reaches us on Earth after 8 minutes. So a photon that was released from the surface of the sun took 8 minutes to reach you here on Earth. Now, what that means is that if the sun was to suddenly disappear, you would not know until 8 minutes later. Suppose that you recorded on your watch or your clock that the sun had disappeared at 12 p.m. Actually, it had disappeared when it was 11:52 a.m. What this means is that we've got to be very careful in interpreting the readings of two clocks which are not in the same place. To explain this point, consider this observer who is looking at these 5 clocks over here and sees them as showing exactly the same time. But are they actually at the same time? The answer is no, because the light from the first clock had to travel this distance over here. But the light from the second clock had to travel a lesser distance. Light from the third clock had to travel a still smaller distance, and even less for the fourth and still less for the fifth. What that means is the light that entered her eye from these 5 different clocks actually started out at different times from these clocks. So this one over here is actually at an earlier time than this or this or this or this. To make the point still clearer, the observer is looking at these 5 clocks over here. She sees the first clock at 10, the second at 11, the third at 12, and so forth over here. Now the fact is that the light from this clock over here had to travel a certain distance. This had to travel more, and this still more, and this still more, and this the most. So, although these clocks were synchronized, yet this one will appear earlier than this, or this, or this, or this. Now here is a way in which we can synchronize all the clocks in an inertial frame, that is, set them to a common value. Here I have 5 different clocks placed a distance d apart from each other, so they are equally spaced. They're all at rest with respect to this observer here. And let's take the clock at the center as our reference clock. So, using the time of this clock over here, we'll set the times of this clock, this clock, this, and all other clocks. To make things a little more convenient, let me take this distance d to be 1 light second. So that's the distance that light travels in 1 second. Now suppose that at time t equal to 0, that is according to this central clock over here, a pulse of light is sent out from here. That light travels, of course, in both directions, and just as the light reaches the two clocks, this one is set at t equal to 1, and so is this set t equal to 1, and of course the time over here is no longer 0, it is 1. So this clock, and this clock are showing 1 second, 1 second, and 1 second each. Now, of course, the photon continues towards the next two clocks, and soon as it arrives there, we know the time is 2 seconds for this one. So now this is no longer 1, it is 2, and this is 2. Similarly, this is 2, and this is 2. So all the clocks now are at time t equal to 2. That is the common time for this reference frame. Now in 2 dimensions, you can imagine that there'd be a grid of clocks. So you would put clocks here, 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 here. So then if you were to take this as the reference clock, then this would be synchronized, so would this, and all the clocks that there are. In 3 dimensions, of course, you would have to imagine a cube, but there's no difficulty. This is how you would synchronize clocks in 1, 2, or 3 dimensions. Now that we have a procedure for setting clocks in any inertial frame, let's look at this particular one. So consider this to be at rest. Let's call this the frame S. Some event occurs over here, and it has coordinates t and x. So the event happened at time t at position x as measured in S. If there's another inertial frame, let's call that S prime, that's moving towards the right at speed v, then that same event will have coordinates t prime and x prime. Of course, I hardly need say that the same procedure that was used in S for synchronizing clocks was used in S prime also, and that's how we arrived at t and t prime. Now, since this is moving with speed v, gamma is the usual 1 over square root of 1 minus v squared over c squared, and in the previous lecture we had derived the Lorentz transformation, which says that the coordinates measured in x, t and x, and the coordinates measured in S prime, t prime and x prime, are related in this manner. Now suppose that 2 events happen. The first event happens over here at time t1 and x1 according to S, and t1 prime, x1 prime according to S prime. So obviously x1 prime and t1 prime are got from x1 and t1 in the usual manner using this. Take now a second event that happens over here. Its coordinates are t2 and x2 as measured in S, and t2 prime and x2 prime as measured in S prime. And so, obviously, x2 prime is this, and t2 prime is this. Now let me define delta x prime as the difference in the spatial coordinates as measured in S prime. So delta x prime is x2 prime minus x1 prime. Similarly, I'm going to define the difference in times delta t prime as t2 prime minus t1 prime. I'll do exactly the same for the difference of spatial coordinates as measured in S and of the difference in the temporal coordinates or the times as measured in s again. Now suppose I take the difference between x2 prime and x1 prime as given by this and this, then obviously delta x prime becomes gamma into x2 minus x1, that's delta x, minus v into t2 minus t1, that's delta t. And similarly, delta t prime is gamma into delta t minus v over c squared delta x. So what this is saying is that if I have these two events, then the difference between the spatial coordinates and the time coordinates transforms exactly as we had seen earlier. Well, of course, this x prime was x prime minus 0. So this too was a difference, but this is more explicit, and we're going to use this to understand when events are simultaneous in a given frame and when they are not. Let's now come to the relativity of simultaneity. So, as before, we have two frames, S and S prime, and two events that occur, the first at T1 and X1 according to S, and T1 prime and X1 prime according to S prime, and the second one at T2 X2 according to S, and T2 prime X2 prime according to S prime. Here is the Lorentz transformation for the differences delta x and delta t. They're related to delta x prime and delta t prime. Now suppose that these two events are simultaneous in S. What that means is that T1 and T2 are exactly the same, and hence their difference delta t is 0. If delta t is 0, then look over here where I'll put this delta t equal to 0 and see what I get for delta t prime. Delta t prime is gamma into minus v over c squared delta x. So delta t prime works out to be this. And that's not 0. Unless, of course, delta x is 0, which means that the two events happen at the same place according to S. And so, what we've discovered is that two events that happen at the same time according to S do not occur at the same time according to S prime. There is a difference which is then proportional to the velocity, proportional to delta x, and that's most certainly not 0. Of course, it also works the other way around. Suppose the two events are simultaneous in S prime. So S prime sees this event and this event happening at the same time, which means T1 prime is T2 prime, the separation delta T prime is 0, and now we know the inverse Lorentz transformation. In other words, we can go from delta x prime and delta t prime to delta x and to delta t. All we have to do is change v into minus v. And so let's look over here. Delta t is gamma into delta t prime plus v over c squared delta x prime. And here, delta t prime is 0. So we get delta t is gamma v over c squared delta x prime. Again, this is not 0 unless the two events occur at the same position as measured by S prime. And so the Lorentz transformation is telling you that simultaneity is relative. To make still clearer the relativity of simultaneity, let's work out a problem. So here is an observer. This is a frame that's fixed with respect to him. And now, as he watches, there is an explosion. This is followed by a second explosion. Now the question is, if there's another observer who is moving, is there any chance that he will see these two explosions as having occurred at the same time? To begin, let's remember that this is the time axis and this is the position axis, so that's t and x over here, and there's t prime and x prime over here. So those are the coordinates as seen by this observer. Now let's say that the first explosion happened at t equal to half units and x equal to 1 unit. So this is 1 unit of distance from here to here, and that the second one occurred at t equal to 2 units of time and 2 units of distance. So delta x, which is x2 minus x1, is 2 minus 1, which is 1 unit of distance, and delta t is 2 units of time minus half unit of time, so that's 2 minus a half, which is 3 over 2. Now we remember that the Lorentz transformation says that delta t prime is gamma into delta t minus v over c squared delta x. And this v, of course, is the speed at which this frame is moving. Now, if we want the two explosions to be simultaneous in S prime, then delta t prime has to be 0, which means that this over here has to be 0. In other words, delta t must be equal to v over c squared delta x. And so v will be c squared into delta t, and now delta t is 3 over 2, so that's 3 over 2 divided by delta x. But delta x is 1, so v is equal to 3 over 2 c squared. So in the units that we've chosen, the velocity v turns out to be this. This observer will see the two explosions as having occurred simultaneously, although this observer sees them as having occurred at different times. Let's now revisit time dilation using the Lorentz transformation formula that we had derived. So, as before, we have two frames. Here's S prime moving this way at speed v. As usual, we have the Lorentz transformation equations, which by now you ought to have memorized by heart. I'm going to put a clock in the frame S prime. Now, this is the 0 position of the clock, and when this needle reaches this position, the 0 position, let's suppose that a flash of light is sent out in both directions. So, a pulse goes out this way, and a pulse goes out that way. Then, 1 unit of time later, this clock has arrived at this position here, and a second pulse of light goes out in both directions, this way and this way. Two events have happened, and they have happened according to S prime at the same position. So delta x prime is 0. The clock has not moved in the frame S prime. However, there was a time difference delta t prime, which is equal to 1 unit of time. Now let's put delta x prime equal to 0 in this equation. And so we have delta x equals v times delta t. Now I'm going to put delta x equal to v times delta t into here. So we have delta t prime equal to gamma into delta t minus v over c squared into v delta t. And now this is gamma into 1 minus v squared over c squared times delta t. But you recognize that 1 minus v squared over c squared, this here is 1 over gamma squared. And so we have gamma into 1 over gamma squared, so that's delta t over gamma. And so what we've shown is that delta t is equal to gamma delta t prime. So as viewed from the frame S, a time delta t will have elapsed, which is equal to gamma times delta t prime, which is of course gamma, because delta t prime is 1. And so, although according to S prime, 1 unit of time has passed, but according to S, gamma units of time has passed. So in effect, this clock, as viewed from this frame, appears to be running slower. Now what about the other way around? I'm now going to put the clock in the frame S and view it from the frame S prime. We're now going to do exactly the same thing. When this clock is in this position, the 0 position, a flash of light is sent out this way and this way. Now, after 1 unit of time has elapsed in S, another flash of light goes this way and this way. Well, let's repeat the analysis. So, what we have is 2 events which have occurred at the same place, the same point in S, and so the separation is 0 in X, and the separation is 1 unit of time as measured in S. Now let's look at this equation over here. It says that delta t prime, that is to say the separation as viewed from the S prime frame, is equal to gamma into delta t, let's call it delta t, this is actually equal to 1, minus 0. Because delta x over here is 0. And so from this equation we get delta t prime is equal to gamma delta t. And this is saying that if 1 second elapses in S, gamma times 1 second elapses in the frame S prime. And so the observer in S prime is going to say that the clock in S is moving slow. You see the symmetry? S accuses S prime of having a slow clock, S prime accuses S of having a slow clock. And they're both right, because time is not absolute, time is relative, time depends upon the state of the observer and the observed. Let's also revisit the Lorentz contraction using the Lorentz transformation formula. So once again, we have 2 frames, S and S prime. There's an observer in S, and S prime is moving towards the right at speed v. Let me put a rod in the frame S prime, and this rod has proper length L. So L is the proper length, which means it's the length that is seen by somebody who is moving with the rod. So imagine an observer who's traveling with the rod. He sees the rod as being L. But now let's ask, what is this observer here, Mr. Garfield, going to see for the length of the rod? Well, obviously he's got to see the ends of this rod here and here, and the light from here and here has to arrive simultaneously in his eyes or in his camera. And so it's necessary that delta t be equal to 0. Light from here and light from here must arrive at the same time in his eyes for him to know how long this rod is. Also, delta x prime, which is the separation in the S prime frame, is L. And so now let's put that into this formula over here. we get immediately that delta x prime, which is L, is gamma into delta x. And so delta x becomes L over gamma. That is to say, this observer will see the length of this rod as L over gamma, and that, of course, is the Lorentz contraction. Moving objects appear shortened in the direction of motion. Now let's see what happens when you have an observer in S prime and the rod is placed in S. So now this observer is looking at this rod, and now let's figure out what's happening over here. So for him to see how long this rod is, he's got to see the ends, and the light from the ends has to reach his eyes at the same time, which means that delta t prime is equal to 0, and the proper length of this rod in the S frame is delta x equals L. So now let's look over here. Delta t prime is 0. Therefore, delta t has to be v over c squared delta x. Let's put that in. So delta t has to be equal to v over c squared delta x, which is v over c squared L. And now, because we want to ask what is delta x prime, that is to say the length as observed according to this observer, well, we can then find that out. That's delta x prime equals gamma, delta x, which is L, minus v into delta t, but delta t is v into v over c squared L. And so that's gamma into L into 1 minus v squared over c squared. But 1 minus v squared over c squared, as before, is 1 over gamma squared. So this is gamma over gamma squared into L, and that's L over gamma. So again, the observer is going to see the stick moving in this direction and shortened to amount L over gamma. So again, the Lorentz contraction. The notion of an invariant interval is extremely important to relativity theory. But before coming to relativity, let me take an ordinary reference frame. So here's the x direction, y direction, an observer who's now looking at 2 points, this and this, separated by a certain distance. So let's call the coordinates of the first point x1 and y1, and the coordinates of the second point as x2 and y2. If I define the difference between the two x's, let's call that delta x, that's x2 minus x1, and similarly delta y is y2 minus y1. So delta x is the separation in the x's, delta y is the separation in the y's, and I can then write down the distance between the 2 points, or rather the square of the distance, as being delta x squared plus delta y squared. Now let me take a different coordinate frame, one that is rotated. So the observer has also rotated with the frame. Now this is the x prime axis, this is the y prime axis, and so the coordinates of the first point have become, in the new coordinate frame, x1 prime and y1 prime. The coordinates of the second point are x2 prime and y2 prime. And so similarly, let me define delta x prime as x2 prime minus x1 prime, and delta y prime as the difference of the y's. Now, again, the length squared will be delta x prime squared plus delta y prime squared. Now, this over here and this over here are both the square of the length of this line. That line or that interval has not changed its value as a result of rotating the observer. And that's why we call delta S an invariant interval. It does not change when the observer changes his reference frame. So the point is that delta S is what we call an invariant. It's also called a scalar quantity, and we'll have use for this later on in our lectures. With that warm-up, let's come to relativity theory, beginning, of course, with the Lorentz transformation relating delta x and delta t to delta x prime and delta t prime. Delta x is, of course, the separation between two events that happen at different places. Delta t is the difference in times. Now let me define a quantity which I'm going to call delta s squared as follows. It's c squared delta t squared minus delta x squared. For now, don't worry about why I've defined this particular quantity, but note that I did have to multiply delta t with c in order to get a distance, and so this here has dimensions of length squared, just like this has dimensions of length squared. If I had not multiplied by c squared, then I would have been adding the wrong dimensions. Similarly, let me define delta s prime squared as c squared delta t prime squared minus delta x prime squared. And now I'm going to show that delta s prime squared and delta s squared are the same. Let's begin. So delta s prime squared is c squared into delta t prime squared, but delta t prime I'm going to take from here, and so that's gamma squared. Then I open this out, I get delta t squared minus 2v over c squared delta t into delta x, and then square this, so I have plus v squared over c to the power 4 delta x squared. And now I'm going to subtract delta x prime squared, taking delta x prime from here, and so minus gamma squared into delta x squared minus 2v delta x into delta t plus v squared delta t squared. Now notice over here that I have c squared. When I take that in here, I get minus 2v delta t delta x. On the other hand, this minus comes in here, makes this a plus, and so this cancels against that. So let's write this out. This is c squared gamma squared, and let's look at this over here, delta t squared here, and there's delta t squared here. And so I can write this as 1 minus v squared over c squared delta t squared. And then there's only this term and this term left. So that's minus gamma squared. That's here. And here I have c squared and c to the fourth. So I get 1 minus v squared over c squared delta x squared. But then this over here is 1. That's because gamma squared is 1 over 1 minus v squared over c squared. And similarly, this here is 1. Therefore, this becomes c squared delta t squared minus delta x squared, and that's exactly delta s squared. So we've proved that delta s prime squared and delta s squared are exactly the same. In other words, this quantity is exactly the same whether you view it from the s frame or the s prime frame. And therefore, delta s or delta s squared is a scalar or an invariant, and this is going to be a very useful fact. To understand this better, let's look at this in terms of a space-time diagram. So here is the usual coordinate system. There's x and there's t. One event happens, that's at t1, x1, a second one at t2, x2, and if we define delta x as x2 minus x1 and delta t as t2 minus t1, then this is what we will call delta s. And this delta s squared has been defined as c squared delta t squared minus delta x squared. But note that there's a minus over here. Earlier on, we had used Pythagoras' theorem and said this distance squared plus this distance squared is equal to this distance squared. But here it is this minus sign which is essential for delta s squared to be an invariant. What this means is, suppose one was to take a different set of axes. So we view this from the frame S prime, where the coordinates are t prime and x prime, and so we write it like this. Although the coordinates have changed, yet the invariant distance delta s prime squared, which we proved equal to delta s squared, this is c squared delta t prime squared minus delta x prime squared. This thing over here, which we're calling the invariant length, does not change when you go from frame S to frame S prime. It's useful to characterize invariant intervals according to whether they're positive, zero, or negative. So here are two events, one here, another here. Here's the invariant distance or the invariant interval between them. And now there are three possibilities. The first is that delta s squared is positive. If it's positive, we call it time-like. And what that means, or the reason that we call it time-like, is in that case, c squared delta t squared is bigger than delta x squared. So in other words, the separation in time is bigger than delta x over c. A second possibility is that delta s squared is equal to 0, and we call this light-like. We call this light-like because in this case, c delta t is the same as plus or minus delta x. In other words, a photon released from here has arrived over here. The distance that it traveled, delta x, was c times delta t. A third possibility is that delta s squared is negative, in which case we call it space-like. And that means that c squared delta t squared is less than delta x squared. Now the important thing is that if delta s squared is positive, in other words, if the invariant interval is time-like in one frame, then it's time-like in every other frame. And similarly, if it's light-like in one frame, it's light-like in every other frame, and the same for space-like. So that means that some things do not change. Causality is a fundamentally important concept in physics. We say that two events are causally connected if the first event causes the second to happen. So, for example, if there's a gun which fires a bullet, now, let's suppose that there is a spatial separation between the two events that's equal to d. So d is the distance between the gun and the bottle. Let's calculate the invariant interval now. So delta S squared is equal to c squared delta t squared minus d squared. Delta t is the difference in times between the second event and the first event. And now, if this bullet is traveling at the speed v, then d is equal to v times delta t, in which case delta s squared will be c squared minus v squared into delta t squared. Since v is less than c, therefore this is going to be positive. Now, here's a question. Is there some frame in which the bottle breaks first and the gun fires later? The answer is no. Our common sense is upheld. And here's why it happens. Delta S prime squared is the same as delta S squared, and delta S prime squared is, of course, going to be exactly the same, except that here we will have the velocity of the bullet as viewed in the S prime frame, and delta t prime will be the separation as viewed in the S prime frame, and delta S squared and delta S prime squared have exactly the same value. So, although in the frame S prime, which is moving with respect to S, the observer will see a different time that separates these two events and a different separation in space that separates these two events, nevertheless, it will still be that this event shall cause that event. And that holds as long as these two events are causally connected, which in turn means that delta S squared is positive. But if delta S squared is negative, then that need not be true. Let's see why. So delta S squared, which is c squared delta t squared minus d squared. Now this d, imagine this to be so large, let's say that this is on the other side of the galaxy, so that d is bigger than c times delta t, in which case this is negative. Now, the bullet cannot exceed the speed of light viewed from any frame. And so if this is negative in one frame, it's negative in every frame. And that says that if you have a gun firing and a bottle breaking, there cannot be any causal relation between the two, which means you could have a situation where the bottle is broken first and the gun fires later, because this event had nothing to do with this event. These two events were so far away from each other in space that even light did not have the time to travel from here to here. What is disconnected in one frame is then disconnected in every other frame. Imagine living in a world where the speed of light was not 300 million meters per second, but just 300 meters per second. In that case, we'd be seeing strange things everywhere. For example, suppose that I was moving towards you at 200 meters per second, that is 2/3 of the speed of light, and I threw a ball towards you at 200 meters per second. you would not see that ball coming towards you at 400 meters per second, as one normally expects. You would see it as coming at some much lesser speed. How much would that speed be? For this, we will do a calculation in the next lecture, and we will learn how to add velocities together relativistically.